This work focuses on inventing and comparing the neural network-based approaches in the specific application domain of software security, specifically for securing cryptographic code. These are the publications I achieved during my PhD research. Recent years, we've observed the increasing threat caused by cryptographic vulnerabilities. Cryptographic vulnerabilities refer to those caused by improper or flawed implementation of cryptographic functionalities. By tracking the most common CWE, which stands for Common Weakness Enumeration, discovered last year, we found that cryptographic issues top the board. And the top 4 CWE entries are all related to cryptographic vulnerabilities in some level. The cryptographic issues, inadequate encryption strengths, and the use of broken or risky cryptographic algorithms definitely fall into this category. And the exposure of sensitive information may also relate to certain mistakes in cryptographic implementation. The root cause of the cryptographic vulnerability is that writing cryptographic code is not easy for developers. It often requires security expertise and knowledge to correctly use these APIs. As shown here, the insecure and secure versions of code may only have minor differences. There are many security rules to comply with. For example, the first one, it requires to use certain strong cipher algorithm, and the second, it has to use API sequence to generate the cryptographically strong random numbers. And the last example, it requires to do a necessary check, the hostname verification at some key point in the authentication. Without knowing this knowledge, developers are very likely to misuse these cryptographic APIs and hence cause vulnerabilities. Developers do need help for secure coding. Based on a survey, it shows that 2/3 of developers admit to shipping code with vulnerabilities. Many academic solutions also verify these bad practices and point out multiple reasons, including insufficient secure priority or awareness, the tight project deadlines, or lack of security knowledge. To aid this situation, developers need help from tool support for detection and or secure code suggestion to help them write code. Therefore, to help developers write secure code easier, the vision of my dissertation is to develop a secure code generation system that helps developers generate secure code suggestions based on neural networks. This work requires the intersection of security, deep learning, and programming languages. Specifically, we have several objectives. First, we focus on the foundation. We care about how to harness deep learning techniques to deal with programming languages. Second, we care about the security. It requires the security guarantee that the neural networks are learning on secure code. Another important aspect is the accuracy. To improve the accuracy, we need to identify and address the specific accuracy challenges of secure code suggestion. We've done lots of work surrounding these objectives. Here, I summarize our achievements briefly. First, we conduct a coding embedding measurement study. We compile 6 types of embeddings trained by ourselves on cryptographic code. Our comparative experiments demonstrate the significant impact derived from program analysis and the embedding vectors. We successfully achieved an accuracy boost from around 56% to 92%. with the help of our depth web embedding. And furthermore, we realized an industrial strength cryptographic vulnerability detection tool that is highly frequent and efficient with the large scale code screening. It guarantees that the code we feed into neural networks is secure. Finally, we make contributions by recognizing and addressing the program dependence specific challenges. With our specialized neural network design, our solution, referred to as multi-high-LSTM, achieves best accuracy around 99%. And next, I'll briefly talk about the new opportunities brought by artificial intelligence and the current trend of programming language modeling. There are many code completion plugins claiming driven by AI technique. However, our test shows that their capability of recommending the correct cryptographic APIs is highly limited. For example, a state-of-art code completion tool, CodeDota, fails to differentiate two code snippets with minor differences, and they require different predictions. However, CodeDota always recommends the same suggestion for them. Due to the similarity between the natural languages and the programming languages, the current neural network-based programming language modeling highly rely on the approaches designed for natural languages. Nowadays, big companies have led the trend of training larger and larger language models with more and more data. For example, from the natural language model BERT to the recent published switch transformer and Wudao 2.0, the model scale has grown from millions of parameters to trillions of parameters. This also influences the programming language modeling domain. The state of art are trying to gain improvement by training larger and larger model. However, increasing the scale is not the panacea, especially for the task with special requirements on security and accuracy. This also verifies by our experiment. We fine-tuned the two state-of-art language model, CodeBERT and Graph CodeBERT, published by Microsoft. They take source code as input. The difference is that Graph CodeBERT append extra data flow information with the source code input. And the two language models only achieve relatively low accuracies, less than 60%.
Yeah, I apologize that sometimes recording, oh, never mind, it's still recording. I apologize. Because sometimes when you reshare, the recording stops, but I see it's still recording.
Okay. And for comparison, our solution achieves an accuracy more than 90%. We will introduce our method later. Many fundamental questions need to be answered. Instead of increasing the scale in a brute force way, we do need a deeper understanding of why some solutions fail and what's the domain-specific accuracy challenges are. Therefore, our work aims to answer questions from the three important aspects. A question about the foundation, how to represent the programs in a way that neural networks can comprehend. And from the accuracy perspective, what are the accuracy challenges in the specific task? Finally, we care about security, how to guarantee the code suggested by neural networks is secure. This is the roadmap of our contribution. We laid the foundation by a measurement study to evaluate important design choices in the process of code embedding. And to improve the accuracy, we identify the accuracy challenges and address them by specialized neural network designs. And finally, we also use a high precision detection tool to guarantee the code we learn is secure. These are the related publications. Next, I will introduce our work about the code embedding measurement. how do neural networks comprehend languages? Languages need to be first transformed into numeric vectors so that neural networks can take them as input for the following calculation. This vector representation is important and makes differences. For example, the traditional way represents language tokens as one-hot vectors, which reflect a bad comprehension. With this approach, every language token has a randomly assigned index and correspond to a one-hot vector that include all zeros and the only one at its index dimension. However, these one-hot vectors are independent to each other and fail to reflect any relation between words. On the contrary, an example of good comprehension is like this. An embedding approach vectorizes the language tokens in a way that their semantic and syntactic relations are preserved. Intuitively, we can see the distance between the vector men and women is similar to the distance between king and queen, and so do the verb tense pals, walking walked, and swimming swim. And if we track the close vector of the word apple, we would find the near words are also related ones, such as Mongo, IBM, and Microsoft. This good comprehension is very helpful and can result in a better accuracy with less training data. How these embedding vectors are produced by well-designed neural networks and the training tasks. The majority of the embedding solution rely on a context-based vectorization idea. For example, to embed the word neuron, its surrounding word in a large text corpus are collected as shown here. And these surrounding words are used as the prediction labels to produce the embedding vectors for the input word neuron. Intuitively, the vector of a word is shaped by its context, which satisfies our reading experience that words with similar context will have similar meaning. And in this case, they result in close vectors. However, the context-based embedding has problems in the code base. The challenge is that the surrounding code statements may not relate to each other. For example, when these are two API method and constant sequences extracted from the left source code. According to the order, we found the two adjacent API methods actually have no influence on each other. And on the contrary, this constant is passed here, acting as the argument used by this method, but the two elements locate far away from each other. And this phenomenon, we call it coding entanglement. The entangled relation suggests the necessity of pre-processing for code embedding. Here we summarize a general workflow of code embedding. Usually the first step is pre-processing. Program analysis is applied to transfer programs into various intermediate representations. And then the tokenization is applied to cut these intermediate representations into token sequences. After that, the token sequences are embedded by the context-based embedding to produce the neural vectors for each single token, which we call it token level embedding. And this is not the end. To further take use of the entire sequence, we can further apply our language model to take the entire sequence as input and produce neural networks given the sequence level input. And these neural networks, we call these neural vectors, we call them sequence level embedding. According to this workflow, there are multiple choices when performing program analysis, token level embedding, and the sequence level embedding. To understand them, we conduct a systematic measurement on these embedding options. First of all, we care about program analysis. We wonder how much program analysis guidance is necessary. Specifically, we include 3 types of program analysis choices, resulting in the bytecode slices and the dependence paths, respectively. First of all, we extract the API and the constant sequences directly from the Android bytecode. And then we apply the interprocedural program slicing, which is a program analysis strategy on top of the Android bytecode to produce the program slices across method. Furthermore, we construct an API dependence graph on top of the slices and extract the API dependence path for embedding. We choose the 3 types of sequences because they reflect an increasing level of program analysis guidance. Second, we care about token level embedding. We measure how much accuracy we can gain from the token level embedding. On top of the 3 program analysis process, the sequences, we apply the skip grand training, which is a representative embedding approach used by Word2Vec. The results are 3 types of token level embeddings, byte2Vec, slice2Vec, and depth2Vec, respectively. Furthermore, we measure how much accuracy we can gain by applying the sequence level embedding. To obtain the sequence level embedding, we perform an extra pre-training after the token level embedding. A transformer neural network is pre-trained with the masked language modeling task, which is designed in the natural language sequence level embedding BERT. The pre-trained transformers are preserved to produce the sequence level embedding byte BERT, slice BERT, and depth BERT, respectively. Overall, we have 3 groups of comparisons. First, we compare between bytecode and program slices and API dependence paths. And then we compare the token level embeddings versus one-hot vectors, which means without token level embedding. And finally, we compare sequence level embedding versus token level embedding, which means no sequence level pre-training is here. We evaluate these different options with a downstream task that is cryptographic API suggestion. We extract the Java cryptographic code from nearly 80,000 Android apps collected from Google Play Store. In the first experiment group, we care about the research question that what are the accuracy input of token level embedding obtained on bytecode slices and API dependence paths, respectively. We train the LSTM sequence model and LSTM sequence to sequence model to suggest the next API method or the next N API method, respectively. The neural networks are trained under different conditions for comparison, including different program analysis choices, different both the embedding or not embedding option, and the different model sizes. This figure in the upper left is the accuracy trained with one-hot vectors, which means without embedding, and the bottom is the accuracy trained with embedding. By comparing them, we found that the bottom is higher than the top, which suggests the effectiveness of applying the embedding vectors. Another obvious observation is that the group of dependence paths achieves higher accuracies than the group of program slices, than the group of bytecode, so which shows the substantial improvement derived from program analysis. At last, we also found that increasing the model scale helps the accuracy as expected. This figure, which is the accuracy of suggesting a sequence of API method, also confirms these major observations. Next, we did a fine-grained analysis on how significant this accuracy boost derived from embedding vectors and program analysis and a larger model size. we measure the accuracy impacts derived from token level embeddings by calculating the accuracy difference. The accuracy difference is the accuracy with embedding minus the accuracy without embedding under these different conditions. We found that the most significant accuracy improvement is achieved on program slices, at most around 12%. And on dependence paths, the accuracy improvement is smaller at most 6.5, but still effective with the sufficient model size. However, on bytecode, there is no obvious difference observed by applying the embedding. So we conclude that the token level embeddings can significantly improve the accuracy, but it requires necessary program analysis, support, and sufficient model size. Next, we visualize the accuracy impacts derived from program analysis, specifically the program slicing followed by the API dependence graph building. By tracking the two figures, we found that program analysis always helps. Both of the two program analysis strategies had substantial improvements, no matter with embedding reflected by this row and without embedding reflected by this row. Overall, the average accuracy improvement reaches around 36% with embedding and 32% without embedding. Next, we also show the.
I have a question. Sorry, yeah. So when you do program slices, can you remind me how you extract the slices from the program? Do you do it based on the data flow or control flow, or how do you do that?
I think both majority is the data flow. Right? Program slicing is analyze the data flow from like our target and extract all the dependence related code.
Okay, and API dependency will be a subset of the program slices because only includes like API calls in the statement.
Yes, and one more difference is that they directly connect which API is depend on which API.
Okay.
We also show the accuracy impact of a larger model. Although we double the model size 3 times, but we found the accuracy benefit from a larger model is smaller and smaller. And overall, the accuracy is improved by around 5%, which is much smaller than the embedding vector and the program analysis. We want to know what are the most effective strategy for accuracy improvements under these different conditions. So we calculate the accuracy improvements from program analysis, embedding vectors, and model size, and visualize the maximum improvements with the corresponding color. And by tracking this figure, we found that most of the times program analysis brings the most significant improvements. And on dependence path, in our experiment that there is no further program analysis choice available. The embedding vectors is a better choice than increasing the model size to improve the accuracy. We also compare between applying the sequence level embedding versus the unpre-trained transformer neural encoder, which means no sequence level embedding is pre-trained. And in these experiments, we also cover different conditions of program analysis and the different model sizes. The results are shown here. The left figure is the accuracy trained without sequence level embedding, and the right one is the accuracy trained with sequence level embedding.
Could you maybe like 1-2 sentences on sequence level embedding? I know you explained it briefly earlier, but maybe
yeah. Compared with the token level embedding, sequence level embedding takes the sequence level input. That is means every vector is generated by considering entire sequence instead of the just one token. like these two figures also confirms with our confirms the trend.
So like how big is the sequence in our case? It's the API call.
In my case, this API method sequence like is around like 10 to 20 the distance.
Does that include the arguments or just the name of the API?
If the arguments appear, we will include them. But if there is no argument, then we don't have it. We observe similar trend compared with group 1. That is, both the 3 strategies improve the accuracy, and by tracking the maximum accuracy boost, and we found that program analysis is still the most effective accuracy improving measure, resulting around 41% advantage. And the difference is that this time the second effective measure is increasing the model size instead of training the sequence level embedding. The sequence level embedding, although there is improvement, but the improvement is very slight, less than 1%. Therefore, we conclude that in that case, sequence level embedding is not that useful considering its expensive pre-training cost. And we perform another experiment on a new advanced data set following the cross-app split setting. Our formal experiment follows the within-app setting. Follows the within app split setting, which means that the training sequences and the testing sequences may come from the same app. In the new cross-app setting, it guarantees that our model is trained on one group of apps and tested on another group of apps. This confirms whether the embedding is effective on new apps. The two figures are the accuracies trained without the sequence level embedding and with sequence level embedding on new app sets 3, 4, 5, 6. We use multiple app sets to reduce the bias, and these app sets are apps from different categories. We found that if we calculate the accuracy improvement derived from the program analysis and derived from the sequence level embedding, it shows that program analysis is still most effective strategy, resulting in at most 21% accuracy for the new apps. And this time we found sequence level embedding is more useful on these new apps than on this existing app in the group 2. It has a more obvious impact compared with the within app setting in group 2. We briefly summarize our key takeaways. First, our experiments highly recommend to use program analysis pre-processing. It shows that with program analysis processing, it can improve the accuracy from 56% to 92%. And also our experiment shows token level embedding can also improve the accuracy. On slices and on dependence paths, it shows 12% accuracy and around 4% accuracy boost. Compared to then, sequence level embedding shows much more slight accuracy improvement. Next, we introduce our work focusing on the specific accuracy challenges. We present specialized neural network designs to overcome the domain-specific accuracy challenges. To further improve the accuracy, we need to understand what the programming language specific challenges are. Let's take a closer look at the accuracy achieved by LSTM neural network with our program analysis and the depth work we just introduced. We break down the accuracy into two separate groups: the accuracy of known test cases and the accuracy of unknown test cases. The known and unknown means whether the test case, specifically the API dependence path, has appeared in the training phase. We found the bottleneck is the accuracy of unknown cases, which is much lower than the other group. By tracking the composition of the failed cases, we also found that the majority of the failed cases are unknown cases, together with the known cases that occurs at a low frequency in training sequences. The frequency, we mean how many times this API dependence paths have appeared in the entire data set. Like we do find that there are some paths more common in the training sets. This can be understood as there are some coding patterns are more likely to be used by developers. And however, these low frequency ones are also important as we care about the correctness of our suggestion. We checked the low frequency cases and the unknown cases to see what causes the failure. By tracking the wrong prediction, we found a common phenomenon. That is, the wrong prediction is often from some highly frequent subsequences. For example, there is an API sequence ABCDF, and when give the input ABCD, the model is expected to suggest F, however, generates the wrong prediction E. We want to learn where does this wrong prediction E come from. If we count the statistics of certain subsequence of the input followed by E, such as DE, CDE, or BCDE, we would find at least one of these subsequence occurs highly frequently in the training data set. In one word, this model relies on a subsequence to make the decision instead of the full sequence. We describe this phenomenon as global dependence challenge. By the term global dependence, we refer to the dependence predecessor locating a bit far from the prediction location, sometimes even out of a local method. So it often requires the inter-procedural analysis to collect it. We demonstrate this phenomenon here. These are the API sequences we extracted from the training data. And although a global dependency is collected, it is the neural networks is difficult to recognize it, not only because it's far location, but also because there are some extremely frequent patterns. The pattern ABCDE is a subsequence appearing again and again in the training sequences. This actually dominates the model. When ABCD comes, it always predicts E, ignoring what happens before. And therefore, when a global dependence appearing before the frequent pattern and requires a different prediction, the model cannot deal with it. We describe this phenomenon as infrequent patterns are shadowed by frequent variants. We present a solution called high-LSTM to solve this challenge. Specifically, the reason the frequent pattern ABCDE influences the infrequent pattern DABCDF is that they have a long shelled part. So the key to fix this issue is to let the model differentiate the two sequences, YABCDE and DABCD as a lesser time step. However, this is difficult because this model has been supervised by so many identical labels as the former steps. Therefore, our solution is to add an extra parallel fully connected layer here to only accept the last token as a supervision signal. And the original fully connected layer is still kept here for the recurrent output of the entire sequence. This kind of like this layer is used to tell the model the difference between two sequences, while this layer is used to keep the similarity between the two sequences. We combine the two layers and generate to form a new hybrid loss function composed of the sequence level loss and the token level loss. In summary, we customize a new loss function. Intuitively, when the low frequency pattern gets a wrong prediction misled by the high frequency ones, our new loss function will give a stronger signal to correct it due to the extra part. Next, we evaluate our health TM on 5 different app sets to reduce the bias. The first one follows the within app set setting, and the others follows the cross app setting. We found that the known cases are the majority cases in the test set. However, the cross app setting has a much higher ratio of unknown cases, which might suggest that the cross-app setting is more challenging and more meaningful to reflect the inference capability of model. Since our health TM has a hybrid loss, we compile it with 2 intermediate versions, the LSTM with token level loss and LSTM with sequence level loss. These are the results of the 3 models. We found that for both of the accuracy on all cases and accuracy on known cases, our health TM outperforms the other LSTM models. However, on the accuracy of unknown cases, our health TM is a little lower than the LSTM with sequence level loss. However, the difference is very slight if we check the 2 numbers. We continually to experiment on 4 new app sets and found that in this experiment, our health TM achieves the best accuracy for the accuracy of all cases and accuracy of unknown cases and accuracy of known and unknown cases. And especially for the accuracy of unknown cases group, our health TM result in a big improvement compared with the 2 LSTM models. We show a case study to validate the effectiveness of our health TM. The left side is a test case getting a wrong prediction by the regular LSTM. We found that the wrong prediction is from another sequence showing in the right side, which only differs the left one in the first token. And by tracking the frequency of the Xiao, the subsequence followed by the wrong prediction or the correct prediction, we found that the subsequence followed by the wrong prediction is much more frequent than followed by the correct prediction. This is the reason why the LSTM cannot generate the correct suggestion. However, our health TM is able to generate the correct answer for both of the case. Next, we introduce another program-specific challenge caused by multi-path dependence. There are some functionally similar APIs that share most of the dependence contact. However, they are not interchangeable. For example, there are 2 API method. Both of them are used to transform the encrypted byte array into a string, but they are not interchangeable, and which one to use is determined by the corresponding decoding APIs. Like we visualize this phenomenon here, G1 and G2 are 2 functionally similar APIs, and most of their dependence paths are identical. So if we take input as the single path, like P1 and P2, the model cannot tell which one to use. Therefore, to increase the distinguishability, we take multi-path as the input to tell the model which one we should suggest. Hence, we present a multi-path architecture that takes multiple dependence paths as input in parallel, and each dependence path is taken by a single high LSTM and produce a vector called path embedding. And all the path embedding are aggregated later by a pooling layer to generate the overall optimal suggestion. To avoid the path explosion, we limit the number of paths and only select a few of them for prediction. Here we demonstrated here, and this figure is the API dependence path. Every node is API method or constant, and we record the data flow information in the edges. For example, which variable is out from this node and which variable is flow into this node. And our path selection algorithm traverses this entire graph with a greedy strategy, which means at each branch, we will try to cover the maximum of different variables with minimum number of paths. Our solution called multi-high-LSTM is equipped with two specialized neural network designs, the high-LSTM and the multi-path architecture. We conduct an ablation study to compare the multi-high-LSTM with some intermediate solutions that removes certain designs. For example, the high-LSTM without the multi-path architecture and the multi-BERT, which is replace the high-LSTM with a BERT neural network. And the result is shown here. We found that for the overall accuracy, our multi-high-LSTM is the best, outperformed the other three models. Interestingly, we found that it seems our multi-path architecture has some side effect on memorizing the known cases. But we still found the high LSTM outperform the DeepBERT in terms of memorizing these known cases. Moreover, we found that for the unknown cases, our multi-path architecture has a substantial improvement effect. We found that the multi-high-LSTM compared with the DeepBERT result in a 27% accuracy boost on the unknown cases. And we compare with a state-of-art academic tool called SLAM that take use of N-gram model combined with the RNN neural network on the object history they obtained. And the result shows that our multi-high-LSTM achieve an accuracy around 91%, which is much higher than the 77% achieved by SLAM. And we also do a manually comparison by comparing the state-of-art commercial tool Codota, which is an IDE plugin, with our tools. We tested more than 200 test cases on Codota and found it can only has an accuracy around 65%. And on the contrary, our solution can reach the accuracy around 89%. I want to briefly summarize our contributions of this work. First, our solution, multi-high-LSTM, substantially outperforms the state-of-art SLAM and Codota by 18% and 50%, which is a substantial improvement. And by the ablation study, we found that our design, the multi-path architecture, excels at inferencing the unknown cases. With the multi-path architecture, the multi-LSTM and the multi-BERT improves accuracy for unknown groups by 11% and 36%. And also, we found the high-LSTM also has advantages compared with two regular LSTM models. Finally,
so yeah, I have a question. So have you looked at GitHub Copilot?
Yes.
Is it fair to compare our work?
Yes, I will mention it at last because GitHub Copilot just online last month, and we do some preliminary tests, but not the systematical comparison. But one thing I want to mention is that GitHub Copilot claim that they are based on a language model called X, and we compare with another language model. I mentioned the CodeBERT and the Graph CodeBERT, and they are the same category.
Okay, that's fair.
And finally, I want to and furthermore, we have a cryptographic API misuse detection tool to guarantee the security of our work. Since the details have already been introduced in the prelim, I will only mention some key points. First is that this is a detection, and we think detection is still an important part of the entire system because with a high precision detection tool, we can remove the vulnerable code from the learning data and guarantee the data quality. And we use program analysis for this detection tool because it is more reliable and explainable than the neural network-based approaches. Due to the special requirements of the big data and the nature of learning, our detector actually has a higher requirement on its precision and scalability. And this work achieves an industrial strength, precision, and scalability with the help of like a high precision refined slicing algorithm and a scalable design on support of the Oracle Parfait, which is a scalable framework. Finally, we achieved many contributions, including a systematical measurement. We revealed the impact of program analysis, token level embedding, and the sequence level embedding. We also published our pre-trained embeddings for future usage. And we also identify two unreported accuracy challenges caused by the global dependence and the multipath dependence. And we have two specialized design to address them. And overall, our solution reaches an accuracy at around 99%. And finally, we also include the detection part. I want to highlight the most important takeaways we learned from this work. First, learn from our experiment. We found that program analysis is very important, and with the help of program analysis, even a small neural network can defeat a larger neural network. And second is so that we found that actually increasing the model size is not the only option. And from most of our experiments, it is even not effective than like program analysis or embedding strategies sometimes. And finally, we found that programming languages require special attention on recognizing the program dependence instead of memorizing the source code sequences. We want to mention a few promising future directions. First is the real world deployment, which is important. They do have some engineering side challenges we need to solve. For example, how to apply the program analysis in real time when developers is editing. And second is we can increase the generality of our work by extending this systematic measurements on more API libraries beyond the cryptographic related ones. And another interesting and important direction is that we need to promote the interpretability. Maybe we can conduct more case studies and experimental evaluation to understand the capabilities of the existing language models. Finally, is like what Xiao mentions, that considering the most recent progress from some commercial tools such as the GitHub Copilot, which is online in last month, and we found that like it is worthwhile to do more systematic experiments so that we can understand how well and what are the strengths and weaknesses of GitHub Copilot. Due to the time, we don't have we don't have time to do like the thorough comparison, but currently based on my manually test on Copilot, the first thing I want to mention is that Copilot is very powerful because it can generate a long code snippet, like the entire code block for certain functionalities. However, I do find that there are some shortcomings need to be improved. For example, I found the code generated by Copilot sometimes is vulnerable. They generate some very common vulnerable examples we can find online, for example, in the online post or for demonstration purpose for me. So I think that Copilot actually, they don't have like a quality control on the learning data, so that there are some bad code appear frequently, and it also recommended to us. Another thing is that I found sometimes Copilot's, the suggestion is not very accurate. Not very accurate, I mean that they generate some related code, maybe use the group of API I'm interested. However, they have some inconsistent parts from like my context. So actually it is not what I exactly want. So I would say that Copilot is a good is a good tool to generate some learning materials, like to generate some example code. But if you have some customized need, maybe Copilot is still need to improve.